So this is essentially the nature of an initial demonstration of the potential for an alternative technique for glucose sensing. And as Clark mentioned, I'm really here standing in for Megha, who couldn't be here. So the paper is essentially going to introduce you to the background and motivation for why you want to look at an alternative technique, and particularly an ultrasound-based technique for glucose sensing. Discuss some of the methodology involved and why it can be applied to this particular problem. We'll go into some of the details of the prototype that was constructed to validate and validate the principles and demonstrate an initial proof of concept, and then point out opportunities for future directions. So ultrasound-based techniques, of course, have been widely applied to a variety of problems, and Sister Conference probably has a lot more papers on the applications of ultrasound-based techniques to areas such as non-destructive testing and in an imaging modality to scanning acoustic microscopy. There are some advantages here that in terms of the way ultrasound essentially interacts remotely with materials, and that allows you to obtain some interesting characterization of material properties and differences in material properties that are probed over length scales that could range anywhere from submicron to macroscopic. And in an imaging modality, of course, looking at optically non-transparent systems is sometimes of interest, where sometimes the optics might interfere with the physical environment of the specimen being probed. And so, again, acoustic microscopy sometimes has interesting complementarity to conventional optical microscopy-based methods. Okay, so this work really builds on the wider application of ultrasound for materials characterization, and there have been a number of techniques that have been developed in the past. Some of these are shown here. These are typically applied at much larger length scales and macroscopic length scales, and some of them combine resonance-based techniques and spectroscopic techniques to probe material properties. They're applied to a range of problems. For example, this is a setup that's used, it's called resonant ultrasound spectroscopy, that's used to essentially infer material properties of macroscopic samples, typically used by geologists to probe things like, material properties of rock samples and things of that sort. But the applications can vary quite a bit, so going all the way from detection of explosives to things like, in fact, there was a transactions on ultrasonics paper that talked about looking at water content in leaves. So quite a wide area of applications. So if you confine the sort of the specimen space, there's some interesting information to potentially be gathered by applying these sorts of techniques. Okay, so that's the wider field of ultrasound based materials characterization, and the previous sort of very brief encapsulation of the previous work in the area. We get into glucose sensing. Again, there are a wide variety of techniques applied here to detect glucose in samples, and of course this is one of the biggest applications for biosensing is in fact glucose sensing. This is an example of a glucose monitor that's used by diabetics, and it's usually typically based on electrochemical sensors, and there are some methods that are based on optical sensors that are employed as well. But these techniques are limited in terms of accuracy, the fact that they're not cannot be used often in a continuous sampling mode, and are quite cumbersome for whoever was using it in this a good likelihood that at least some of us in the room know somebody who's a diabetic and knows the issues with using these sorts of devices for regular monitoring. So the ability to be able to potentially non-invasively and remotely probe for glucose concentrations might be of interest, or at least to be able to do it with very low sample volumes in a microfluidic device, and in a continuous reading format. So this is essentially the first step towards maybe ultimately integrating this in a form that might be used for continuous sampling, and really, as I said, is a proof of concept demonstration of the potential for using ultrasound-based techniques in a scalable, miniaturized format for glucose measurements that potentially might overcome some of the issues with these other techniques. Okay, so Vega's listed a number of different potential advantages of using ultrasound for this sort of method. So a lot of you are probably familiar with gravimetric sensors. Again, small molecules like glucose, very difficult to actually get to work with that technique. But again, with gravimetric sensors, you've got issues in terms of surface preparation and surface contamination and so forth that you have to deal with. So if you could potentially integrate all of that into a compact platform, that would be quite interesting. Okay, so that's the objective of the paper here, and essentially what's going to be shown is the initial results in a very simple microfluidic device that's got a pair of ultrasound transducers used to make measurements of acoustic cavity resonances in the microfluidic channel, and infer from that the material properties of the analytes that might be flowing through that channel. And this essentially builds upon work that was published in Ultrasonics at the end of last year. That's where the validation was conducted for samples on a sort of a macroscopic length scale. So these were, this is essentially the simplest formulation of a model that involves the sample of interest sandwiched between media through which you've got propagation of plane waves, in this just one-dimensional plane waves with number of assumptions built in, including the fact that there is no, though these are lossless media, for instance. But this fairly simple model is a good starting point to set up an analytical basis for the technique. So if you were to take a simple 3-layer model and model the response of the system, you could work through a closed form expression for the transmission parameter as a function of the acoustic impedance of the media and the dimensions involved. And at a sort of characteristic set of frequencies, you of course will set up cavity resonances in the sample, depending on the material being probed. You'd see different sort of finesse factors associated with those resonances. So again, work on sort of a theoretical scale was presented at IUS a few years ago, looking at different types of samples and looking at just the analytical modeling basis to describe this. So this is the wideband simulated response. So you over a range of about 3 megahertz, a number of different cavity resonances that are seen, and then you can start to zoom in on some of the peaks in between. So this is the case for glucose sensing, again simulated using that model for a range of concentrations in a microfluidic channel that's got a dimension of 125 microns. and this is being probed over frequencies. In this case, the cavity resonances would be at a higher frequency, on the order of tens of megahertz or so. Okay, so in fact, the prototype devices were constructed with off-the-shelf transducers, which had lower operating frequencies, so to scale up the dimensions a little bit. And these were measurements that were initially done in larger cuvettes to show just the fact that they aligned reasonably with the predictions from the analytical models, so that if you change the concentrations, you could, of course, change the shift the associated resonances. And then there were a couple of microfluidic type devices built, so PDMS on glass device that had a channel that was a little bit larger to accommodate the lower frequency transducers. And then because you also have issues in terms of the resonances being set up across the glass PDMS layer, and those sometimes do interfere in that frequency range. There was this another device that was built with metal sheets that sandwich the sort of microfluidic device in between. Okay, so for these device dimensions, the analytical model that was shown would present a transmission response that would look like that, and then you would end up with for the metal device, you see that in fact the experimental results do line up. This is just in the presence of just water, so no glucose. And then with the glass device, you have a mismatch because of the interaction of the modes that are set up in that composite stack. So that's the experimental setup with the two transducers and swept frequency measurements, and so fairly simple setup there. The frequency range of interest is in the lower frequency end, so in the low megahertz. That then spaces the response away from the resonance of the metal plate itself. And so that's what the raw data looks like as you go from DI water to varying concentrations of glucose and magnitude and phase responses. And you can then infer from those measurements effectively the effective speed of sound in the medium, which over this fairly wide range of concentrations does track linearly with concentration. So then application to other types of analytes. So again, this is a technique that could be applied widely to other analytes as well. So for instance, fructose shows a very similar sort of response. Okay, so with that, I think summarize the results here. So essentially this work demonstrates the feasibility of using a broadband swept frequency ultrasound technique to detect glucose in microfluidic channels. The underlying analytical models are in broad agreement with experiments, but of course further work is needed to capture some of the deviations that you saw between the models and experiment. Of course, ultimately you would want to integrate the transducers with the microfluidics, and then maybe integrate some sample pre-processing up front to allow you to get some contrast and selectivity to multiple analytes. So that's the plan looking ahead for Mega, is putting that all together. So for those of you who are in the tutorial, you might, for instance, have PMOT devices that might be integrated into these microfluidic channels, and you could also integrate, because it's a fairly simple topology as far as the detector itself goes, you can integrate a lot of the sample pre-processing that is now conventionally done using microfluidics up front to try and improve analyte selectivity. Okay, so that's it, and of course, yeah, yes, thanks to all our generous sponsors, including the frequency control community for support. Of course, maybe I was looking forward to being here and being part of the Women in Engineering event, so hopefully she can make it next year. Thanks very much.